Okay, for about 5 or 6 weeks on the underwater explosion topic, of course, the amount of the time is not enough, but I expect you capture the essence of underwater explosion. That's what I expect. So even if I cover the first few chapters, the remaining chapter is beyond underwater explosion, is combined with the structural dynamics area. So as you captures about 5 weeks, 5 to 6 weeks amount of the index should be sufficient for the time being, okay? So you have fire a little bit, you have a gas explosion a little bit, you have underwater explosion a little bit. As I look at like Abdullah's November project on the gas explosion is a very interesting small report he prepared with the Hyunchul. Looks very good. So you can, in that case, he talk about all the combined effect, explosion, gas explosions, and fires, and all that. Okay, now this is Wednesday, so 2 hour this week, 2 hour next week. Then Friday, I'll spend 1 hour, then I can sitting at the corner, then you present, maybe 10 to 15 minutes for your project. Doesn't matter whether fire, whether underwater explosion, or combined gas explosion with the fires, with the index, and we'll do some I want to see your presentation. I try to think how to let your mouth open and talk. This is a very good chance next week. You can speak up, talk about your project. So it's very, very good. Okay, that's what we want to do. This part is remaining of section 2.4. I didn't cover, but I'll talk a little bit, then I'll move on. So as I mentioned to you, 3 parts this semester. We cover 3 parts: fire, gas explosion, underwater explosion. All the characteristics are quite different, but I'm pretty sure you gain some insight into the phenomena, but they are not really, if you look at carefully, independent each other. It's all connected. It's really in the art of the explosion. Fire is always there. So gas explosion can be connected very easily, and underwater explosion can be connected with the fires and so on, okay? This wave is really interesting, and it shows the general. This was one of the Navy report, but it's not classified report, so it's showing the general wave action. This is a form, okay, form like a styrofoams. And this is a steel plate, and this is styrofoam. This is really very interesting type of the material that wave cannot transmit through, okay? It's something like air also. And of course, think this is media is water, and this is a foam. So which means in the water, there is air pockets in there. Whenever you have an air pocket, the wave, shock wave, does not able to penetrate through the foams, okay? Because we learned this week the water and air interface problem. Shock wave in the water does not transmit into the air. Very little. As we saw the example problem, only the fraction of the 1 megapascal out of 1,000 megapascal passes through. But that doesn't, we don't even recognize, we don't feel it. So here this is a foam, but steel is concerned, it transmits the wave right through. It's almost transparent, okay? So charge explode right here, and this is opening, okay? And this is just drawn into 2D. You can think of as a 3D also. So at the time of explosion, of course, a shock wave will propagate. So this portion is the wave passing through the hole here. So this portion is incident shock wave. Then it's going to really propagate through. But this is continuation of this incident shock wave and close in the backside of the foam. This wave doesn't go through here. Does not go through the foam. And this is called the diffraction wave. What the diffraction wave is, if you turn on the flashlight in the darkness, for example, you see the light go through. In the behind of the obstacle, in this case is a foam, if you stand here, you still see the light there. You can see the things because of the diffraction effect. Diffraction wrap around. Okay, that's a part of the wave. And of course here the wave reflect as this at the time of explosion, you know, the spherical wave will generate, propagate. It hits, then it will reflect, because this is act as air, and this is reflection wave. And the reflection wave here, see, it wrap around the corner here. So this part is called the diffraction, same as here, okay? And the other side, at the corner, it diffracted right from here, going through, it closes. Wave never jump. It's always close each other. And this side is, looks a little bit complicated, but the reason I put this in is to show you so-called the head wave. Whenever you hear the head wave, there is no energy in the head wave. Very, very little energy, almost no energy when you hear the head wave in the water. Look at this closely. So now, as the spherical wave hit the steel, it will penetrate through. This portion is penetrate, so it's a transmitted wave. It has a continuity reserved here, okay? And it goes, and of course, as a shock wave is moving forward, then the reflection wave from the steel plate, of course, occurs. This is a reflection wave. Right at the tip, this is acoustic wave in the water is, of course, you know, something like the 1,500 meter per second. But the acoustic speed in the steel is much faster, which is something like how much in the steel? What would be the acoustic speed in along the steel? Huncho, what would be it? We went through in chapter 2.2 or 2.3. Did we go through? Maybe not there. It's something like a solid steel is about 25,000 feet per second. You divide it by 3.3, then how much is it? About 8,500 meters per second. Extremely fast in the steel plate. Okay? Steel plate, when you tap it, so wave, it generates the wave, and it wave propagate along the steel. It's about 8,000 meters per second, very fast. But as I showed, pay attention here. This is the only reason. As shock wave propagate in the, of course, radial direction, this alpha angle, okay, I just connected, and as it propagate farther, this point will move here, then this alpha goes higher, alpha angle goes higher, then eventually goes away. Then surface wave along the plate is C over the sine alpha. As alpha angle is getting higher, C over sine alpha, this C over sine alpha value is getting larger than C. So acoustic speed along the plate suddenly take over the speed of the acoustic speed in the water. This C is in this case, C is acoustic speed in the water. And this C over sine alpha goes down as alpha is increasing, right? And at some point, the acoustic speed along the steel plate, by the steel plate, well, not the by, in the steel plate, that let's call the CS. That CS is larger than this C over sine alpha. C is acoustic speed in the water. Then the end of the wave is suddenly moving faster. It zaps and goes through faster. So that means it gives an effect to pull the wave here, this reflection wave and transmitting wave right at this corner, and it just move fast along the plate. So it generates suddenly another wave in front of the reflection wave and transmitting wave, and it move like this guy move this way, this guy move that way. Not much energy, almost no energy in there, head wave. This effect is something like in submariner, when they are inside of the submarine, then explosion occurs. Then they can hear explosion occurs someplace. Then suddenly they feel a little bit, feel the wave hit by the head wave. But in fact, that was not really the energized head wave, energized wave, but it's just a false wave. Sometimes this is called the false wave, not realistic wave. Then they feel, oh, something has been gone, so they feel it's gone. In the very next moment, then rear shock come and hit. That's what the thing is, but physically head wave does not affect the target. So this is the reason I put this on. And this is the case, similar, but this is a plate all the way, and how the head wave is generated at the end. And this is the case similar for effect on affected by head wave, water, and this is charge, and this is incident shock wave by the charge, and image charge, I could put it here, and this is image charge, reflection by the charge, which means you can put the image charge and you can draw the shock wave front. This is a wave front by the image charge, so it's a reflection wave. Then I can draw this point is pulled along here because acoustic wave in the ground is much faster than C naught over C1. C1 is acoustic speed here in the seabed, and C naught is acoustic speed of the water, and this point got the effect to pull. Of course this point will move, but it looks like there is another wave in front of this bottom reflection wave. Another wave will generate and go propagate, and this wave, so-called head wave, will hit the target, but they feel, oh, something came in, but rear shock coming afterward. So it's called head wave or false wave. But in any other book, they don't talk about the head wave. Only for I think naval application, they talk about the head wave here. And the diffraction wave, shadow zone occurs behind the obstacle. Okay. Read it through, and this is kind of the last equation in chapter 2. The wave propagation velocity in the water. This is acoustic speed in the water is a function of salinity. Salinity is the salt content, okay? So salt content, you're talking about parts per thousand. The range of S salinity is about 34 to 37. So the value is almost fixed. If you go Indian Ocean or Atlantic Ocean, Pacific Ocean, this value changes a little bit. But you can say 35 or 36, that's really fine. And acoustic speed in the water is also function of hydrostatic pressure. As you go deeper and deeper, acoustic speed is changing, and the temperature is another parameter. But hydrostatic pressure is a secondary parameter. It's not the major player. So you can neglect that. Then C is equal to 4577 plus 11.5 T plus 4.6 S. This is a unit dependent, and this is C is feet per second. Temperature is in Celsius scale. S is just a unit number between 34 and 37. So if you have to consider more accurate acoustic speed in the water, this is the equation, you can use it. This is not for acoustic wave propagation study. The focal point for this equation is really for explosion relevant, okay? When you talk about the underwater explosion with the surface ship or submarine, this is perfect equations, okay? But if you talk about the acoustic velocity, caustic effect and all that, then that's, you have to consider the effect of hydrostatic pressure, because it depends on, like a depth is 20,000 feet. That's deep water. So that situation, of course, affect on the acoustic speed. So that you have to. But in underwater explosion research, this equation is a very good equation. Then you can use without any reservations, okay? Okay, that's remaining part of chapter 2, and we started already chapter 3. I want to finish, this is all done, this is done, and of course this is done, okay? And this equation is empirical equation, and this is done. And of course exponential decay function for the shock pressure, and this is T1, and 0 0 is reference 0 is explosion, time of explosion. Then T1 is the time the wave reached to the target, and here this note is this is not the original. You modify after you modify this, because I put as I showed yesterday, red line happened to be there, but anyway, P max and the theta is, what do you call the theta? Decay constant, right? And which is really the defining the decay rate of exponential decay pressure profile. And this is what we did yesterday. And collection of all the empirical equations. So also here, this is energy per unit volume. This is impulse, shock wave impulse. And A4, K4, A3, K3 was in the table as I showed yesterday. And 3.2 I started yesterday, gas bubble behavior and gas bubble pulse loading. And here, this is, what's A max? What's A max? Bongshik, what's A max? Huh? Yongyan, what's A max? Louder. Maximum bubble radius. First gas bubble, that's the largest, right? A max. What's the 33? Abdullah, what's the 33? How you drive a 33? Kyungsuk, what's the where the 33 come from? 33이 어디서 나온 거야? Atmospheric pressure, equivalent hydrostatic depth for atmospheric pressure, 14.7 psi or 1 bar. We did, right? Right, remember? And what's the T here? Jude. What's the T here? This is first period of gas bubble. Sometime you have to compute the gas bubble radius. And I mentioned to you this, the Monday, total energy, about 53% energy takes by the shock wave. The remaining 47% comes with the gas bubble. Gas bubble is much slower. Shock wave hit and goes away. But gas bubble oscillation is slow. That gives really damage to the target, damage to the ship, damage to the submarine. And 47%, shock doesn't carry everything. Only about 53%. This is really experimental observation. And this varies. So I mentioned to you, you don't have too much worry about this, but this is important. 53% roughly sweep away with a shock wave. The other 47% comes with the gas bubble. And all this phrase is a reminder, and when you have a time, I really want you to read that, okay? Today's bulk cavitation is what I want to talk. Next about 20 minutes. Bulk cavitation. When you hear about the bulk cavitation, cavitation at the time of explosion always occurs near the surface, near the free surface, okay? And this is a free surface. Okay? So I'm going to put the vertical line here. So I say this is charge is sitting right here. Okay, and as you see, the shock wave really propagate in all direction, in radial direction. When the shock wave hit, then this bulk cavitation zone occurs near the free surface like umbrella shape. This is upper cavitation boundary. Upper, this is upper cavitation boundary. And also this is due to like mostly starting with the incident shock wave, but afterward due to the rarefaction wave or tension wave, what happens is there is also lower cavitation boundary occurs. Something like this. It's not very good. It's of course axially symmetric. It's a 3D. You can rotate this guy. So it's like a big umbrella kind. It's not that really fat. The calculational result also shows in next few pages. And cavitation, when you hear about the cavitation, you can think of the bubble, okay? Propeller cavitation, lots of little bubble. But here, this is not the propeller, the cavitation. This is really cavitation due to the explosion in the water. And all here is like a vapor. It's like a vapor. You can simply say pocket with very misty water bubble. Okay, no pressure inside here. Pressure is equal to 0 inside this bulk cavitation. This is a bulk cavitation. Okay? So then, at the time of explosion, if you have a chance to look down, the underwater explosion process, then you can see the surface of the surface of the water is suddenly white, and white zone is spreading fast. Then of course a plume occurs, but eventually it doesn't stay long, as it just spread quickly, then close. The cavitation zone closes because water is surrounded surrounding, water is surrounding the cavitation air pocket, then it closes so quickly. Huge, like umbrella zone, cavitation zone. Then it closes. In the water, in the explosion process, whenever it closes, it has so-called closure pulse. Closure pulse. Okay? It's a secondary shock wave effect. Bang! And closes, okay? So when surface ship is sitting here, okay, when another shock wave coming here, shock wave cannot penetrate through this bulk cavitation zone, of course, in the instant sense. So it doesn't affect the ship sitting on the bulk cavitation, but phenomena is so quick. It's not in terms of the millisecond, but you can explain in terms of the fraction of the second, okay? So this is called the bulk cavitation. So this is what. But this secondary pulse is not that big, okay? Incident shock wave is what straight goes up, coming like this, and when this bulk cavitation closes, it could generate another peak. Pulse means another peak, but this height pressure is not big compared with this. But if you look at the area under, you may not be able to neglect, because area under is called what? Impulse. This impulse is related with damage, okay? Because this could give you heavy damage to the target. So that you have to think. So here my note, lecture note has two different sections. Remember, bulk cavitation. This is this is section, I'm going to say 1 to explain the bulk cavitation. There is another section behind or front to really derive the equation for upper cavitation boundary and lower cavitation boundary, front or behind of the section. This section is what? 3.3. We look around there. What's the section here? This is the section. So it's a whole derivation of bulk cavitation equation is in right after 3.3. Then you can really look at, as you have a time or wants to know some more detail, derivation of upper cavitation and lower cavitation boundary, okay? So that's what I'm going to show you. So when I say this is like a vaporized water particle is really trapped in this bulk cavitation zone, is when I say vapor, water vapor, VAPOR, the water vapor can resist on tension around up to 0.3 psi, very small. So rather than dealing with a 0.3 psi, you can look at this way. You pick up any point. If that point, you can compute the total pressure here. If the total pressure that you computed is 0 or below 0, then you can declare this is a cavitation zone, okay? Because the water cannot sustain the tension. Well, it could go something like a few psi below zero, but you don't have to worry. You can say, you know, if the total pressure here goes to below zero, then you declare the cavitation occurs. Then you can draw the upper cavitation boundary and lower cavitation boundary. So you will end up just computing that part, then it's axisymmetric. So you don't have to compute that part, this part. When you rotate, it's going to be the cavitation shown. So this I want you to read. I just put a few words in there. And logics behind is what this graph shows. This is a real charge, and this is image charge. And I draw the line here, then you can determine this intersection point. And incident shock wave is this line here, okay? And this dotted line is surface reflection wave. In other words, you put the image charge here, then you draw the radius from here to here as a radius and draw the line. So this is a surface reflection wave front. Okay, this will propagate, this will propagate. That's a basic wave action. And of course, this is a compression wave, and this is a tensile wave. Think as image charge as the attracting source. It attracting the water particle here. Then wave front is moving downward. All the water particle due to the image charge is shooting toward the center here. Okay. So drawing into the XY plot, this XY plot, this is a whole story to explain the bulk cavitation. Bulk cavitation, inside the bulk cavitation, total pressure is equal to zero or below zero. Water cannot sustain the tension. Below zero means it's zero. Okay? So here, the vertical axis is absolute pressure. Hyuncho, look at here. I can afford to lose anybody here. This is absolute pressure. And this part is what pressure? This part. You know, you could have a target someplace below zero here. Then this part is hydrostatic pressure plus atmospheric pressure, right? So this part always there is a static pressure. When you look at the target point, which is below the free surface, one is hydrostatic pressure up to that depth plus atmospheric pressure, always there, 1 bar, 14.7 psi. So it's there, right? Then bang, then explosion occurs here. It's right up there, then it's shooting up. So from here to here, from here to here is what? Dynamic pressure, right? Due to the shock wave, right? Due to the shock wave, it's a bang. And after that is exponential decay curve, right? Make sense? Yes. Then suddenly there is a negative pressure peak coming down and slowly merging into the zero. What's this? What's this? Juil, what's this? Kolgi, what's this? Tell me. That part is surface reflection wave, surface reflection wave, or tension wave. Surface reflection wave, look at this. It's the first wave reflect from the surface to hit the target. So as you look at, this is reflection wave path, straight up and coming down here, right? So this guy is pressure. I put the gauge right here. This is the pressure, right? This is the pressure profile. And by the incident shock wave is by this, the wave, incident shock wave, straight line, it hit the target first, right? Hit the target first. Then before the target hit is static pressure. When the shock wave hit the target, then shock pressure is added right there. Then shock wave gonna pass through exponential decay and converge to just a nominal pressure, right? But the surface reflection wave, it comes up along here. Then, due to the reflection, it takes along here, hit the target. Compressive wave here. Then from here to here is called the tension wave, or I talked this already a few times, tension wave or rarefaction wave. Or the surface reflection wave. Okay, it's all same. Up to here is a compression wave. From here to here is a tension wave. Tension wave is the wave which pulls the water particle. Water cannot sustain the tension. Okay, so which means it comes right down to zero. So look at this. So water from here to here, water particle try to fly along this line toward the image charge, and the water particle keep trying to shoot as the wave comes down here, keep trying to move. I think this is good enough. Toward the image charge, water particle is moving in the image charge direction, but the wave, tension wave front is moving toward the target. So fluid particle along the tension wave line, fluid particle is moving toward the image charge, okay? But the wave front, tension wave front is moving toward the target. It's opposite each other. It's called the tension wave, rarefaction wave, and so on. That's the wave from this part. So after the incident shock wave hit the target, then it exponentially decay. Suddenly, right at a certain point here, then there is the tensile, the wave coming, hit the target. So it bang down to the P max for rarefaction wave, then reduce down. That's what this portion is. It keeps going up, it passes through, eventually just goes away, get down to zero. There is no static pressure. This is dynamic pressure, which means tension, tensile pressure, okay? Then, right at the, if you add it all together, this is going, start here, bang, no change, bang down, then right at this point here, right at this point, how far after at Tc time. This is called the surface cutoff time, very important phenomena, okay? Surface cutoff time. Surface cutoff time, this is the difference, this is the difference between the cutoff time is the time of the difference between the incident shock wave and the reflection shock wave. Okay, so which means if I say this will take more time, this guy will, incident shock wave will hit the target first. That's let's say T1 right here. And this distance is from the image charge to the target point. This distance plus that distance. You got it? Minus the distance from here to here. So then divided by the acoustic speed. So let's call this distance is R2 and this distance is R1. So the R2 minus R1 divided by acoustic velocity C is the time for Tc, right after the after incident shock wave hit, then Tc time later, the tension wave coming hit the target. So this is important. So here goes up and down here, right at that point, bang, it comes down. If you add this pressure together, if it could come below the zero. If it's below the zero, you have to reset to zero because water cannot sustain the tension. My lips are drying, which means it's desperate to show you. So it's going to go up and down, down. Then when the bubble the cavitation closes, then there is another hump. So this is eventually, this will converge to the nominal pressure. It should be good enough. It comes a couple more times. So here, this is this portion, this cutoff, surface cutoff is right here, okay? Right there. So sometimes when you add pressure to two pressure together, it could come right here or below the zero or way below the zero. You know, the chances are depend on the depth of the target. So for this case, A, pressure greater than the vapor pressure of water, and the cavitation pressure, let's say, could be around here. Cavitation pressure. Cavitation pressure means is really pressure which break the water particle, really breaking the water particle into the molecular level, just breaking off, okay? So that level, which is around the people talking about 304 psi, negative 304 psi, maybe could fall around here. Doesn't mean much, because we are dealing with a dynamic pressure which is much higher. So eventually we reset to zero to declare whether it's cavitated in the water or not. But in the physics, strict sense, it could have here, could have here, could have here, but cavitation pressure could be somewhere along there, okay? And point B is a pressure less than the vapor pressure of water, but greater than the cavitation pressure. If I say cavitation pressure is around there. And the cavitation pressure is the pressure at which the water really breaks off. a negative here, negative few psi. Really doesn't affect. Remember, one thing to remember is cavitation occurs if the total pressure is 0 or below 0. That's all you need. But, explained so much detail in there. And exercise problem, I want you to solve this exercise problem. Simple, very simple. You don't have to submit to do it. Any question, you can talk to me or Higyu. So very easy problem. And next one is a cavitation calculation. And upper cavitation calculation, this is for easiness, upper cavitation boundary. Upper cavitation boundary, for computational purposes, what you have to do is to compute. You can make a really grid, refined like a FEM grid, okay? Then you have to really go through the point by the do loop using your MATLAB code. You can set up the MATLAB code very easily. For this case, total pressure at any point you have to compute. So check out whether that point is, that the pressure at that point is 0 or below 0. If it's not below 0, that point is not cavitated. But if it's below 0 or 0, then you can point, just to put the point there, oh, this is cavitated, the point. So it has 4 different pressure. One is incident shock pressure at the time when the rarefaction wave arrives at the point to be considered. What that means is here is this. What that means is right this point, move, just put the point straight up, that point. At the time of rarefaction wave or tension wave hit the target, which means right that point here. So you have to compute the pressure, incident shock wave pressure, not this point, not the P max, but that point, okay? Then that's what the P1 is. P2 is a rarefaction wave pressure, which means right that point. P max in rarefaction pressure. So what I'm doing here is summing up all the pressure right at the point called the cutoff time. If that pressure is below 0 or equal to 0, you can declare that point is cavitated. So PA, atmospheric pressure. PD is hydrostatic pressure for the depth. When you're summing up, if PT is equal to 0 or below 0, then you declare that point is cavitated. So you have to go through many points, make a grid by the do loop, then you can do that. I'll stop here. Lower cavitation boundary is, this is lower cavitation boundary here. Of course, along the lower cavitation boundary, total pressure is equal to 0. But for detecting this point, use a slightly different technique. That's what I'll show you Friday, okay? Well, then we'll continue. Okay, I'll stop here. It's 10:56. So I'll see you Friday.